floor is yours.
Okay, well, thank you. First, I'd like to thank Sander, for inviting me. I didn't know about this seminar. It's great. I think I'm going to come in the future, or now that I know. And so I'm going to talk about this topic. It's about the Axelrod model. That's a joint work with different people. So Jason Schwensberg from UCSD, Stylianos Karlados from Greece, and Paul-Henri Moisson from France at different points in time. And Axelrod himself, so he's a political scientist and sociologist who is, I think, professor at University of Michigan, and he's one of these first guy in sociology, but with a master's degree in math, who said that we cannot move forward in sociology if we don't use mathematical models. So he designed this model and other types of models. And that's great for sociology. And he's also the author of this very popular book called The Evolution of Cooperation. So that's this guy. And so the Axelrod model is, in fact, even if it's not the terminology used in his paper, that's an example of interacting particle system. So I believe, in view of the audience, that you all know well interacting particle system, so I don't need to define that too much. So in the Axelrod model, you see that's about the dynamics of culture. So we are going to have something like that, a graph with particles are going to be human beings. So that means that typically in the original paper of Axelrod, where I introduced the model, the graph, you should not think of the graph as space, okay, where individual like particles are close to each other. If they are close to each other in space, it's more like a social network, okay, where individuals are connected if they know each other. And so in like a priori, the model can be defined on any graph that we think of a social network, but eventually all the results I'm going to explain are only true in on the integers. I could not do more than the integers. So that's the background. You have a bunch of individuals, human being, again, located on a graph, and they are characterized by their culture. Okay, so you have a bunch of people like that with different cultures. And so you probably heard about opinion models in the field of interacting particle system. And the most popular example is the Wöhler model, where individuals are characterized by one of two possible opinions. In general, you have a lot of different other opinion models that were introduced, called the HK model, the different model. I mean, you have a bunch of models now. And in all those opinion models, the state of each individual is an integer or a real number. So that's something in one dimension. And the way Axelrod defined a culture in sociology, you know, from a mathematical point of view, it's by saying that's a vector of opinion. Okay, so the idea is the following, is that you take several topics. So here, for instance, I have pictures showing music, religion, and political ideas, political opinion. And you can have as many topics as you want. And then your opinion for each of those topics is going to create a vector of opinion that we call a culture. Okay, so a culture, like a cultural dynamics in interacting particle system, is kind of the same as opinion dynamic, except that the state now is a vector instead of a scalar. Okay, and so in the Axelrod model, you are going to have, so the Axelrod model itself is going to be, I translate from discrete time to continuous time so that we can define that on infinite space. That's going to be a continuous time Markov chain with state at time t is a spatial or a social configuration Xt that is going to map the vertex set of the graph into the set that we call set of cultures. So that's 1, 2, 3 up to q at the power f. F is going to be the number of what Axelrod called the cultural features. That's like the topics, like music, religion, politics, and so on. and Q is going to be the common number of options or states you have per topic. So there is some kind of restriction in his model from start, because he assumes that the number of options you have, like the number of possible religion, or the number of possible types of music, or the number of possible political parties are the same, okay? And he calls that Q. That's only to limit the number of parameters, okay? But of course, that would make more sense to allow to have Q1, Q2 up to QF for different topics. And that's what we are going to do eventually. Okay, so that's the state space of the model. Okay, so you have this graph and set of cultures that depends on two parameters, F and Q. Then one way to visualize the process is like that, for instance. So here, horizontally, I have space, or like the social network, that just the integer. The picture is not really a restriction in the sense that I'm only going to give you results in one dimension, and that's all we know so far. And so horizontally you have space, vertically you have those individuals and their culture. So here in the picture, F equals 3 because we have 3 levels. Okay, 1 at the bottom, 2, and then 3 at the top. That means that we have 3 topics, okay, but that can be any number. And Q also is equal to 3 because I'm using 3 colors, okay? So that means, for instance, if you look at the rightmost individual, the way you interpret that is to say that for topic number 1, this individual has the red opinion. For topic number 2, this individual has the blue opinion. And for topic number 3, this individual have the green opinion, okay? And so green at different levels, I mean, same color at different levels don't mean anything. It's just like a color that we use. So now, in his original paper, Axelrod said that the 2 most important mechanisms in opinion dynamics and cultural dynamics in general are homophily and social influence. And so those 2 things, they kind of work as some kind of converse of each other. So homophily is defined as the tendency of individuals to interact more frequently with individuals who are more similar, while social influence is defined as the tendency of individuals to become more similar when they interact. So one means more similar implies more interactions, while the other one means more interactions implies more similar. So they kind of work as some kind of feedback loops. And before the work of Axelrod, sociologists believe that those 2 key components in social interactions, only those 2 key social components would lead a population to consensus. And Axelrod disagreed with that, and that's why he designed his model to argue that you don't always have consensus even if you include those 2 mechanisms. So what's interesting is the way he designed the model to include those 2 aspects. And I believe so. Right now, I worked a lot on like model in sociology, like interacting particle system in social dynamics. And you have a lot of models that include those 2 things. But I believe that Axelrod is the first one who introduced a model that includes homophily. So the way he's including that is by assuming that neighbors are going to interact at a rate equal to the number of topics for which they agree, okay? So going back to the picture, the way you look at that is, you look at the bottom of the picture, I put numbers. Those numbers, they just keep track of the number of agreements between neighbors. So for instance, if you look at the 2 rightmost individuals, these 2 comes from the fact that they agree about topic number 2 and 3, but they disagree about topic number 1. And so that means that their cultural profile match for 2 out of 3 opinions. At the opposite, those 2 ones, they disagree about everything, so there is a 0 here. And so in the Axelrod model, you can think of those numbers also at the rate. at which neighbors are going to interact. So those two ones interact at right 2, but those two ones in this configuration cannot interact. And that's the way he models homophily. And so indeed, that's a good way to model a homophily. You just say, you just assume that the degree of similarities between individuals is equal to the number of topics for which they agree. Okay, so for instance, in this configuration, it's possible that those two individuals interact. For instance, they are going to interact at right 1. When this happens, then you, as a result of interaction, the two individuals are going to get closer in terms of cultural distance, and so that's how you model social influence. So that's done a little bit like in the Wöhler model, where in the Wöhler model, after an interaction, the two individuals interacting fully agree, except that in this case, because it's like the state space is more complex and you have a vector, you are only going to match their opinion only for one of the topic for which they disagreed. Okay, so going back to the picture, if you look at those two individuals interacting, what you are going to do is choose one of the two topics for which they disagree at random. So you choose one of those two ones at random, and then you choose one of the two individuals at random, and this individual is going to mimic the other one for that topic. So in this case, you can have 4 different outcomes that are equally likely. The green here can become blue, or the blue here can become green, or the blue here can become red, or the red can become blue. Okay, so for instance, maybe like the blue here becomes red. And you see that after the interaction, whatever this number was is going to increase by 1, because now you have one more agreement. So except if this number is F, meaning that they already agree about everything, in which case nothing happens. Except in this case, this number after the interaction is going to increase by 1. But the number on the right here, that can be on the left, depending on who mimics who, can stay the same or increase or decrease by 1. Okay, and so in this configuration, after the interaction, the 1 should become 2, but the 2 should become 1, because before the interaction, you see those two ones were blue, so you had 2 agreements, but after the interaction, now those two ones disagree here, and so the 2 here is going to become 1. So you get that. Okay, so is it clear about the way the model is defined? Yeah. So then important question. So yeah, other models we looked at, so that's in the last paper with Paul-Henri Moisson, we looked at a model with only 2 levels. So there are only 2 coordinates for each vector, so 2 topics, but we allow Q to have different values. So we have a Q1 and Q2. I'm not going to talk really about this paper, except just to give the results. Okay, and so then the 2 main questions, if you do simulation of the model, you would see that there are 2 different types of behavior, 2 extreme type of behavior with some kind of Kolmogorov 0-1 law, where you have either fluctuation or fixation. So fluctuation is defined as this, like it's defined like this. It's the probability that basically looking back at the picture, it's going to be the probability that each of those dots is going to change color infinitely often, okay, with probability 1, while fixation at the other extreme means that each of these dots is going to change color only a finite number of times with probability 1. Okay, so it seems, we didn't prove that, but it seems that we have this 0-1 law where we are either in one extreme or the other one, at least for infinite graph, of course. And the kind of the main objective is to know in which case we are, depending on the parameter F and Q, or after in the other model with F equals 2, depending on the value of Q1 and Q2. Okay, so here are simulations of the models. So the colors are kind of chosen at random. It's just done so that different cultures have different colors, but you see that on the left picture, when F equals 3, so you have 3 coordinates per vector, but only 2 possible values or 2 possible colors, you see that the boundaries between cultural domains, they tend to they move. They are like free boundaries. Some of them are stuck at first. You have those vertical lines, but eventually individuals tend to agree more and more. You have those clusters forming, and it seems that on the left-hand side, you have fluctuation. But if you look at the picture on the right, you see all those lines that are stuck. That means that they separate individuals who disagree fully, who disagree about everything, and so cannot interact. And so it seems that at the opposite, when f equals 3 and q equals 3 also, it seems that we have a fixation, according to those pictures. Okay, but again, those pictures are difficult to interpret, so we kind of need to do some mathematical analysis to know what's going on. So many people studied this model. So people from in sociology, but also people in physics, in statistical physics, studied those models using numerical simulation and heuristic arguments, and they came up to this conjecture. So the kind of consensus in the community, scientific community, was that if f is strictly larger than q, so you are up there, then we must have fluctuation. At the opposite, if q is strictly larger than f, then it seems that we have fixation. People didn't say much about what happens when f equals q, because that's kind of a critical, that's kind of the phase transition seems to happen here, and it's not clear what happens there, except some people looked at the case f equals q equals 2, and in this case, they believe that we must have fixation, again, based on numerical simulation and heuristic arguments. So the first paper, so that's this paper in the Annals of Applied Probability, where I look at the process where f and q are both equal to 2, and I look also at some fixation results. In this paper, that's where I explain some construction I'm going to detail soon. So in this paper, the first thing I proved is that when f and q are equal to 2, in fact, you don't have fixation, you have fluctuation. Okay, so first mathematical result shows that the conjecture from physicists is in fact wrong. Okay, and so I looked at their argument. It's not, the problem doesn't come from a mistake in the math or a mistake in the numerical simulation. It comes from the fact that they use some kind of approximation of the model. And then they believe that the approximation was a good approximation of the Axelrod model, but it wasn't, in fact. So first result shows that the conjecture was not correct. So in fact, the phase transition goes here. Okay, it should go down instead of going left like that. So then, second result, that's in this second paper with Jason Schwensberg, where we looked at the two-state Axelrod model. So two-state means that q equals 2, but f can be anything. And so that means that going back to the picture I showed you, that means that you have only two colors. So in this case, we are able to extend my first result, showing that in fact we have fluctuation when q equals 2 for any values of f. Okay, so that's the main thing I'm going to talk about. This is the most difficult result that we have about the Axelrod model. Then next result, with Stylianos Karlados, we looked at the fixation phase, okay, for which values of f and q we have fixation, and we were able to prove the following. So the theorem says exactly that if f over q is less than 1 minus 1 over q at the power f minus 1, then we have fixation. On the picture, all the pairs fq such that this is satisfied are the white dots here. Okay, and of course that keeps going forever. Okay, that's an infinite triangle. Because this condition is a little bit difficult to visualize, we did some basic Taylor expansion also to prove that anything under this line which has slope the solution of e to the minus x equals x, which is about 0.567. Any point under that satisfies this. Okay, so you have fixation under this line, and you have a few points sometimes that are above, but not many. And so that's our result. And also, so if you look at the Axelrod model, of course, it's going to be difficult to have a full understanding of the whole phase diagram, but that would be interesting. You see, there is a gap here. If you look at around what I show with the mouse here, there is a gap here where we don't really know, like from that, we don't know what happens when Q equals 3 and F equals 2. But looking at, again, the result we proved with Stylianos, and redoing the combinatorics, there is some combinatorics behind, and redoing the combinatorics, but more carefully in this specific case, we were able to prove also that there is fixation in this case. Okay, so that's all we know about the original Axelrod model, like from mathematical point of view so far. Then after, the next thing is looking at the model with only 2 topics. But now we have a different number of options per topic, so Q1 and Q2. So in this case, I'm looking at this, basically. I'm looking at this vertical line here, okay? No, this one, sorry, this horizontal line here, where F equals 2. Then when Q1 equals Q2, then we know what happens already. And so that's what I put here on the diagonal. We know, like from my first paper, fluctuation here, and from the third paper with Stylianos, we know fixation here. The question is what happens in the rest of space. So that's something that we looked at in a paper with Paul-Henri Moisson. And in this case, we were able, so something easy to prove, not by using coupling arguments, because you could imagine that you can compare different Axelrod's model with different parameters using couplings, but that doesn't work at all because there is no any monotonicity in those models. But still, redoing the proof, it's easy to check that all the proofs were perfectly fine for all this region, and you can prove that there is again fixation there. Okay, now this is an easy result. What's difficult is to understand what happens here and there, which should be the same by symmetry. It's what happens when Q1 or Q2 is equal to 2 and the other one is larger. And then we were able to prove that. So the theorem exactly says that if Q1 plus Q2 is larger or equal to 6, then we again have fixation. Okay, so if you look at those lines here, it seems that that's the critical thing. It's like, what is the value of Q1 plus Q2? So for 6 or above, we have fixation. For 4, okay, Q1 equals Q2 equals 2, we have fluctuation, but we don't know what happens here. Okay, so that's an interesting open problem. If you want to work on that, that would be the next thing to do. What happens when Q1 plus Q2 is equal to 5? This, we were not able to solve that. Okay, so that's all the results I have. And now I have, like, I don't know, 30 minutes to tell you about the proof.
Nicolas, but this is always in dimension 1 nearest neighbor.
Yes, yeah.
So you have conjectures for non-nearest neighbor or higher dimension?
No, I don't really know. The only work I know that is, I mean, all the work in math about the Axelrod model is what it's what I'm talking about today. The only other work I know is unpublished. It's by a student of Rick Jurett. He worked on that, a student of Rick Jurett who worked on that during his PhD. And he was able to look at the process on some large 2-dimensional torus, but then he wasn't able to prove fixation or fluctuation. But he had something like, if F and Q go to infinity, but in such a way that the ratio is less than something or more than something, then there will be a giant component with the same culture. I mean, that's very, very partial result in 2 dimensions. And this work, for some reason, is not published. That's the only other work I know in mathematics. So after, you have conjectures by statistical physicists, and I didn't follow really, but people in statistical physics studied the model, I guess, on like over graphs, like random graphs, social network, and so on, and they have conjecture about the model. But in math, we don't really know yet. Okay, so now let's look at the proofs. So the proofs are interesting because none of them involves complicated calculation, and all the proofs can be visualized. So starting from now, I'm going to show you a lot of pictures. So the idea that the first idea I used in my first paper was the following. So I started with this picture thinking, okay, so we have the different colors, okay, and different cultures, but remember that the two important questions are whether we have fixation or fluctuation. And to answer those questions, we don't really care about the culture of like which culture people have. What matters is whether they agree or not, and what's the level of disagreement in between them. And so one day I was thinking, well, instead of studying this process, let's study this system of particles. So what I'm doing here is I put crosses along edges at the level in which individuals disagree. Okay, you see that? Like here I have two green, so I have an empty edge, but here I have two different colors, blue, red, so I put a cross, blue, green, so I put a cross. So those crosses, they just keep track of the disagreement. And I was thinking, okay, let's look at how the Axelrod dynamics is going to affect the dynamics of those particles. And let's see if we can do something with that. And the result is very neat. In fact, we can get a full description of this system of particles that behaves like a very nice continuous time Markov chain. And then eventually the problem of fluctuation or fixation reduces to the problem of studying this particle system. And fluctuation is the same, or fluctuation and consensus are the same as saying that you have extinction of those particles, while fixation means that those particles are going to survive in the long run. So let's look at what can happen. So first, it's possible, for instance, that those two individuals interact because they don't fully disagree. And in case they interact, so this green can become blue or blue can become green. So if green becomes blue, then after the interaction, this particle should not be there anymore, okay? Because that keeps track of the disagreement. So this particle should not be there anymore. But you see that here we had an agreement, and now that becomes a disagreement. So that means that this particle is going to jump to the right, okay? At the opposite, if blue becomes green, then the particle is going to jump on the left, okay? And in general, you can prove that this system, you have particles that behave like a system of one-dimensional symmetric random walk, but run at different rates, okay? Because, for instance, if you look at this pile of particles here, meaning that those two individuals fully disagree about everything, they cannot interact. So that means that those particles cannot jump. At the opposite, this particle is going to jump faster, and those two ones are going to jump at a slower rate, okay? So they jump at different rates, but at the end of the day, what's important is to know if they can jump or not. So we have this first thing. So we are going to call an edge where you have less than F particles, a leave edge where you have active particles, and an edge where you have a big pile of particles where everything is occupied, a blockade or frozen particles, okay? And so now the first picture shows what happens if you have a jump of a particle onto an empty edge. Now the question is what happens if a particle jumps onto another particle? And there are two possibilities. So one possibility is here. Let's assume that those two individuals interact, and so you have one particle here, one particle there. If blue becomes green, then the particle here, according to this picture here, should jump to the right, okay? But because green and red are different, eventually the particle jumps here, but those two particles are going to coalesce, Okay, you keep this particle here, so we are going to call that a coalescing event. Okay, so here in this case, you have a coalescing event. The fact that you have coalescing event, if you go back to the story, comes from the fact that before the interaction, the green here and the red here don't match. So because they don't match, eventually this one becomes green and still those two ones don't match. And so you have a coalescing event. Okay, so you may have a coalescing event. But in other configuration, like this one, at the opposite, you see here that the green here is the same as the green here. If those two ones interact and the blue here becomes green, then the particle jumps left, but then you should not have any more particle here. So eventually the two particles are going to annihilate, okay? So whether particles are going to coalesce or annihilate depends on whether before the interaction, the two particles on both sides of the individual to be updated match or not, okay? And so now the tricky question is, okay, but we want to understand, if possible, this particle system without knowing the color, okay? At least when we start from the configuration in which the colors are chosen uniformly and independently from the set of colors. So the question is now, let's assume that we become colorblind, okay? So with this picture, if we know the color, we can tell if there is coalescing event or annihilating event. Now, the problem is, assuming that we become colorblind and we cannot see the color, can we tell whether there will be coalescing event or annihilating events? At least, can we give probabilities to those two possible types of events? And the answer is yes. And that's the neat part of the model. We can indeed put an exact probability on the event coalescing and the event annihilating. And so the idea to prove that is to use some kind of duality ID. So duality techniques for particle system, except that, so I guess you all know at least the dual process of the Euler model, you know, that goes back in time and behaves like a system of coalescing random walk. So for the Axelrod model, you are going to have the same kind of ID, except that the dual process is not useful really, because here I'm just showing you a picture where you have those things that coalesce going back in time. So that's kind of interpretation is that when you follow back in time those lines, you keep track of the ancestor of each opinion. But it's only one layer. For the Axelrod model, you would have a superposition of F layers like that are not independent, that interact with each other. And you would need to know the configuration at each time to be able to know how those things moves. So that's not really helpful in general to study the process exactly like in the same way as the Euler model. But you can still have this idea of, you know, going back in time to keep track of the ancestors and that defines some system of coalescing objects. Okay, so that would look like that, except that I intentionally draw a false picture here. So do you see why the picture is wrong? Here I have time t, and I assume I'm looking at only one level, and I assume that there is a particle here and a particle there, while the other edges are empty. So that's not possible. Like that's inconsistent with the picture of the dual, because the dual here would mean that those four individuals, you know, if you keep track of their lineages or ancestors, eventually they coalesce into one. And so that means that they have a common ancestor here. So this picture would mean that those four individuals should agree, okay, and have the same opinion as this one. But that would contradict the presence of a particle here. Okay, there cannot be a particle here if it's the case. Same on this side, you know. So because we have a particle here and a particle there, that means that this individual on the left here and this individual here should have different ancestors. And same, this one and this one should have different ancestors. Okay, so the picture instead should look like that. Okay, so now because of this, and Claudio, to answer your question, that's why, in fact, we have only a result in one-dimensional nearest neighbor, because that's what we use here. It's also the fact that because of one-dimensional and nearest neighbor interactions, the ancestor of this guy and the ancestor of this guy cannot be the same. Okay, they may have the same opinion, but they cannot be the same people, the same person, because that would mean that all those individuals, all those lines here, they should coalesce, and all those individuals agree, which contradicts the presence of those two particles. And it's not possible for this line here to coalesce with this one without having coalescing events with the middle because of nearest neighbor interaction. Like basically those lines cannot cross without coalescing. Okay, so now that we know this means that each time you see two consecutive particles in your system, then the individual on the left of the leftmost particle and the individual on the right of the rightmost particle must have different ancestors. So that means that their opinions are chosen uniformly at random, okay, from the set of colors, but also conditioned to be different from the opinion in the middle, okay? So from that picture, I can say, okay, I don't know what's going to be the opinion of this one, and same for this one, but I know that their two opinions are going to match with probability, well, the probability that two uniform random variables chosen from a set of size q minus 1 are going to be equal. So that tells me eventually that, going back to this picture, that we must have annihilating events with probability. So you remember, annihilating event occurs if those two ones match. And by the duality idea I just described, that would mean that they must have different ancestors, and their ancestor must agree, but they're also conditioned to be different from the one in the middle. So you get that you have annihilating events with probability 1 over q minus 1. And so that tells you also coalescing events with probability 1 minus 1 over q minus 1. So eventually we have this description. So I started this in the first paper, but I only had a partial description of that, and we fully described this particle system in the third paper with Stylianos. And so if instead of looking at the Axelrod model, you keep track of the disagreement, looking at those particles, you eventually end up with a system of one-dimensional symmetric random walk run at different rates, where piles of size f cannot jump, the other one can jump at different rates. And each time you have a jump of a particle onto another particle, you have coalescing events with this probability or annihilating events with that probability. So that's a system of annihilating, coalescing random walks. And using this, we can prove fluctuation or fixation. So now, let's look at those results one by one. So I'm going to show you the proof for 3 of them. Now that we have this description, the proof is not going to be too long. This fluctuation result now is easy. Now that we know this description, so in this case, what happens is the following: you have f equals 2 and q equals 2. So you have 2 layers, 2 levels, and 2 colors. So in this case, q equals 2. If I go back here, q equals 2 means that q minus 1 equals 1. So that means that the probability of annihilating events is equal to 1. So in this case, you are in the particular case when q equals 2, where you can only have annihilating events. And that kind of makes sense. That means that if 2 people disagree with a third one in a world where there are only 2 opinions, then those 2 people must agree, okay? And so like, if you look at the picture, if you have 2 particles, then clearly on both sides, you should have matching colors, okay? Because you have only 2 colors. So in this case, you have only annihilating events. And so the trick here is so to look at the new particle system where you identify opposite cultures. So in this case, you have 4 cultures: blue, blue, green, 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 blue, blue, green. You identify the opposite ones, and then you realize that any of those 2 here is going to interact, like any of those 2 types of individual interact with any of those 2 types of individual with rate 1. okay? While those two types cannot interact, but that doesn't matter because they're identified, same for those ones. And so you end up with a system where you have only two types. They interact at right one, and it's easy to see that if you have any of the two on the left interacting with any of the two on the right, then one of the two is going to become exactly like the other one. And so eventually, after doing this identification, what you get is the Wöhler model. Okay, so the Wöhler model is hidden behind the Axelrod model when you identify opposite cultures. Once you realize that everything is easy, then we know it's like forever. I think it was even a result proved before I was born that we have fluctuation in the Wöhler model. We know that since a long time. Then this implies, of course, that fluctuation in the Wöhler model would mean here that you go infinitely often from this to that and back from that to this. So fluctuation after identifying cultures means that if you don't identify cultures, then you have even more fluctuation. So we have fluctuation, but then that implies it's easy to prove extinction of the blockades. That means those spikes of two particles, which itself implies clustering and consensus. Okay, so eventually we have the first result here. Okay, then second result, the one with JSON. So this one is much like is more difficult, but that relies a little bit on the same idea. But we use also some symmetry arguments. So the idea is the following: to prove fluctuation. The goal is to prove extinction. It's easy to prove that fluctuation is equivalent to extinction of the blockades, like those spikes of particles here. So the way we start the proof is by saying, okay, let's take a blockade somewhere at time 0, let's say. And then the goal is to prove that this blockade is going to break eventually with probability 1. So the way you break the blockade is, you remember that now you can only have annihilating events. The way you break the blockade, that's by proving that one of the particles around, one of the active particle around is going to eventually jump on one of those three particles, which is going to kill one particle and then free the other two particles. So the goal is to prove that. We fix a blockade, we want to prove that eventually, with probability 1, one of the active particles around is going to break the blockade. For that, we go to the right until we find the next blockade. That's a tiny bit more difficult than that, the construction, but I simplify a little bit and just to explain the spirit. So you go to the right until you meet the next blockade. Then it turns out that because you can only have annihilating events, if you look at the particles in the middle, so of course, on the whole integer, you have infinitely many particles, but between those two blockades, the number of active particles, number of particles here is finite. And annihilating event makes the system parity preserving, okay? Because particles are going to disappear by pair, and so the parity is going to be preserved on not only globally, but at each level. Okay, and so that's the trick to prove that one of the two blockades is going to break eventually. So Q equals 2 means only annihilating event. So the parity before one of the two blockades break is going to be preserved. And so that means that if you have a different parity at different levels, so that's the case here, you have even, odd, 2, 2, 1, okay? In this case, you can think about it. Doesn't matter how those particles are going to evolve. They might form new blockades in the middle or annihilate, but eventually there will be always one free particle. Okay, there will be always one active particle because different parities. And so that means that eventually one of those particles should break the left or the right blockade. Okay, but then by symmetry, that's going to be left before right with probability 1/2. Okay, that's using a symmetry argument. Okay, so let's assume that we have bad luck and eventually the right blockade breaks first, which is not good because our goal was to prove this one is going to break eventually. So the way you prove that eventually it breaks, that's by using some kind of induction. So step 1, you choose the first blockade here. And if you have different parallels, which happens with probability at least 1/2, you break left before right with probability 1/2. So with probability at least 1/4, you are going to break eventually the left blockade. If it doesn't work, okay, meaning different parallels or this blockade breaks first, what you do is that you look at this whole interval, you call it, I don't know, I'm just using this symbol to like have some visualization of that. And then because the set of integer is infinite, you can just keep going forever. And then you start with this interval and you look at the next interval of the same length. And then the next one, and the next one, and the next one, until you see an interval of the same length with exactly the same configuration of particle. Okay, so that's symbolized by this picture or the reflection of it. Okay, so exactly the mirror image of this configuration. Okay, so if this interval is like of length 10, then you look at the next interval of length 10, and then the next one, and so on, until you find same configuration or mirror image. If you have mirror image, which by symmetry is going to occur with probability 1/2, that means that this blockade on the extreme left has its mirror image on the extreme right here. Okay, in which case you can again use symmetry argument to prove that the blockade on the left is going to break with positive probability. So eventually what you have is that you have reflection instead of translation with probability 1/2. Then because of some, independence, I mean, you have to be careful doing that, but you can prove also that the parity is going to be like different at two different levels, again with probability at least 1/2. Okay, and by symmetry, if you have a reflection and not translation, then by symmetry, all those particles in the middle, they are going to move at random and they will break the left blockade before the right one with probability 1/2, which gives you that with probability at least 1/8, you are going to break this blockade eventually before the one on the extreme right. And if it doesn't work, that doesn't matter, because now you call this whole thing again this, and you repeat that. Okay, so you have larger and larger intervals that are increase exponentially fast, but that doesn't matter because they are all finite and your set of integer is infinite, so you can keep on going forever. And then eventually, after a geometric number of trials with success probability at least 1/2, you can break the blockade on the left. So if I put everything together, what we proved is that if you look at one specific blockade in your system, then this construction using symmetry arguments and parity preserving and so on is going to tell you that eventually this blockade is going to break with probability 1/2. This shows that eventually we have extinction of the blockades, and then this shows exactly like before that we have fluctuation and then extinction of the blockade, which is the same as fluctuation, and then clustering and consensus. Okay, so that was to prove this result with JSON. Now the last one, I have a few more minutes to do this. This one is much easier, and in fact, the end of the proof is really like undergrad level probability. So that's the result about fixation. So in this case, of course, we need more colors. If you have Q equals 2, we said that there can only be fluctuation. So I'm going to increase for the proof the number of colors. So now we have, for instance, let's say F equals 3 and Q equals 3 also. It's just for the picture. We don't know fixation in this case, but it's just to illustrate what's going on. So in this case, the spirit of the proof is the opposite. In this case, to prove fixation, we want at the opposite to prove that the blockades survive. And we want to prove that if you have a blockade like that, like this one at time 0, then there is a positive probability that this blockade is never going to break. Okay? If you can prove that, using some like ergodicity and so on, you can prove that there is a positive density of blockades that never break. And so that gives you those like very small cultural domains everywhere, and that shows fixation. So And to prove that, so the starting point was to use an idea due to Maury Bronson and David Griffiths, who use like the same idea to prove fixation for a cyclic particle system. And for in their process, it's the same. They look at one-dimensional nearest neighbor interactions. So their idea was to look at some worst-case scenario where we assume that you could use the active particles the way you want and throw them to the blockades to break the blockades, okay? So we look at this, we kind of ignore space now. We just ignore the fact that, those people are neighbors of each other. We just say we are allowed to take the active particles and throw them onto the blockades to break them as much as we want, okay? And then, in this case, what's going to produce fixation is the fact that now, because Q is equal to 3 or more, then we don't have only annihilating events, we also have coalescing events. So that means that each time you throw an active particle on a blockade, this blockade can swallow this active particle, okay? And then what's going to happen is that if Q is large enough, then coalescing events have a large enough probability so that the blockades are going to act like some kind of vacuum that are going to absorb the active particles. Okay, so that's kind of the spirit of the proof. So now, to prove that rigorously, so again, yeah, fixation would follow from the fact that there is not enough active particles to break all the blockades. And to quantify that, we want to count the number of blockades, the number of active particles, and we need to kind of give some weight to those particles to be able to quantify this statement that that blockades are going to eat the active particles around. So first, basic stuff. At time 0, we assume again that the colors are chosen uniformly at random from the set of Q colors. So you have a match between neighbors with probability 1 over Q, or a mismatch with probability 1 minus 1 over Q. So that tells you what's the density of particles, okay? So that means that, in particular, the initial number of particles at some age is going to be binomial with parameter the number of levels, and with first parameter the number of level, and success probability 1 minus 1 over Q, okay? So when Q is large, you have more particles and you have more blockades and so on. So that's something important. And then after, the question is, which weight should we give to those particles? So we follow the same proof as Bronson and Griffiths, except that now we have different levels and so on. So we had to kind of extend their proof. But then the starting point is just to say that active particles, if your goal is to prove fixation, active particles are bad for you. And so I'm giving to each of them a negative weight, like -1 for each active particles. Okay, so if you have a pile of 2, you have -2. A pile of 1, it's -1. And in general, I active particles with I strictly less than F would give you a weight -I. Now the question is, which weight should we give to a frozen pile? And so in this case, the question is really about how many active particles are going to jump on this frozen pile before breaking the pile. And so this comes from the probability of annihilating events. We know that you have at each collision, you are going to have annihilating events with probability 1 over Q minus 1. And you can prove also using, again, duality techniques that at each jump onto a blockade, whether you have annihilation or not is independent of the past. And so because of that, that means that the number of jumps on a blockade before you break it is going to be geometric with success probability 1 over Q minus 1. Okay, so that tells you that a blockade is going to kill eventually, is going to swallow eventually this random number of active particles. But then once you have your annihilating event, that's going to free F minus 1 active particles. You have F frozen particles that are going to turn into F minus 1 active particles. So that tells you that the correct weight to give should be, for a blockade, should be geometric with parameter 1 over Q minus 1, which is the random number of active particles the blockade is going to kill, minus F minus 1, which is the deterministic number of active particles you are going to create. Okay, now once we are done with that, so next step is a little bit tricky, but I'm not going to detail that. You can use duality techniques, the ergodic theorem, and also some large deviation estimate for the binomial random variable and the geometric random variable to prove that eventually you are going to have fixation if the expected value of the weight of an edge is strictly positive, and the rest is only undergrad level probability. Okay, so the rest is just that. The expected value of the weight is just, well, you just write the definition of expected value, and then you have probability that your X here, number of active particles, is equal to I. So active means that you are less than, strictly less than F, in which case the weight is negative I. So that gives you this term, plus expected value of this random weight, Z minus F plus 1, and times the probability that you have a blockade. Okay, and then that just basic probability, then you end up with the fact that this is this expression. And so if this is strictly positive, according to this theorem, then we have fixation, and that gives you exactly this condition here, F over Q less than 1 minus 1 over Q at the power F minus 1. And that's it, I'm done. It's exactly 10 a.m. here in Arizona. So thank you, and I don't know if you have any question.
Well, thanks, Nicolas. So for a very, very stimulating and interesting talk. Could I ask if there are any questions from the audience?
Yeah, Nicolas. So I've essentially two short questions. What about the existence of non-trivial stationary states and convergence to stationary states? Do you have anything like that?
Yeah, so for that, like we said, fluctuation implies consensus or clustering. So that means that when we have fluctuation, what we know about that is that the only stationary distribution are the trivial ones, okay, where everybody has the same culture. And then for the fixation regime, then in this case, that's like there are like infinitely many possible like configuration that are, you know, like traps, like infinitely many. I mean, no matter how you choose, in fact, F and Q, you can always design your configuration to be a trap. So those, like this particle stem has infinitely many absorbing states. Now, the thing is that in the fixation phase, it's more like if you start from a uniform product measure, then you would get trapped locally in like those absorbing states very quickly. But at the opposite, in the fluctuation regime, what you have eventually is that you have convergence to only one culture, like asymptotically. So clustering. And so like for the Wöhler model, that means that the only stationary distribution would be I guess, Q at the power F configuration corresponding to everybody having the same culture. So that's kind of what we can deduce about the stationary distribution. But it doesn't seem that you have a non-trivial stationary distribution with like that keeps evolving. That's either everybody agrees, or then you have the other extreme where the system gets stuck very quickly. So for instance, you don't have anything like a non-trivial stationary distribution like in the Wöhler model in 3 dimensions or higher. Maybe you have that in 3D, you know, like for this model, but not in one dimension.
Okay, and then my second question will be to uniformizing culture. So assume that you start at time 0 with Bernoulli, but with a larger probability for certain culture. And you would like to see if there is a threshold for which you will fix on that culture. So
okay, so yeah, so we didn't look at that, but obviously the proof with like my first result and the proof of fluctuation with Jason Schwensberg does not use this anywhere. So as long as you don't force the process to fixate by starting from like already an absorbing state, as long as, you know, your initial configuration is random enough, you know, even if you change the probability of different cultures, then everything we proved about fluctuation should still be true. After, for the fixation result, like the construction is still true. I mean, everything, you know, we have in this slide is still true, with only one exception, that would be the fact that initially the number of particles at an edge is binomial. So you would just change that, and maybe also the geometric, like maybe the success probability would change. But most of this proof should still be true. Like most of the construction are still true. And then I would assume that the condition for fixation would be different, but you can reuse most of those arguments.
okay. Thank you.
No problem. Yeah. Any other question?
So I have a question. So you mentioned the time to maybe fixation or consensus. Is there some way to describe the statistics of the time?
We didn't do that. I don't really know. I don't know how we could do that. So of course, again, because the system is infinite, okay, like the time you have to wait until reaching an absorbing state is infinite. Okay, so there will be always active particles somewhere. Now, after, of course, the good question would be, you know, like if you fix one site, then we know that the time at which this site is going to stop changing, which is, I believe, not a stopping time. It's a random time, but not a stopping time, because that depends on the future. Question would be, what is the distribution of this random time? Or at least what is the expected value of that? And this, I don't know. I believe it's pretty short, you know? I mean, if you go back to the beginning, so I don't know, it's somewhere in the middle in my talk. So, but if you go back to that, I mean, look at what happens here. Okay, on the picture on the right, and we are close to the phase transition. You see that you have a lot of activities at the beginning, and very quickly everything gets stuck, and you have some fluctuations somewhere eventually, you know, but the system gets stuck pretty quickly. So yeah, my opinion is that the expected value of, like, let's say if you call t the typical time at which a given vertex will stop being updated, I would say that the expected value of t is pretty small, but like is like of the order of 1, let's say. You know, it's not something that's going to scale like some large parameter. That's just probably pretty small. But we didn't look at that, no. But that's good. You have like interesting question you can answer, maybe. I don't know if you can study me. I mean, I have a question too. In fact, it's, do you think you could study that from like hydrodynamics limits point of view?
I'm not sure, but I mean, there are martingales in the voter model, right? Especially if you're on a finite graph, then the number of opinions of equal to 1 is, I think that's a martingale.
Yeah.
So I wonder if some martingale analysis could be used for the Axelrod model.
I know that Duret and with Cox and Perkins, and after Duret alone, has a lot of results about hydrodynamics limits, about voter model perturbations. I don't know if you've heard about that. So just like some small perturbation of anything that looks like the Wöhler model. So the Axelrod model is not the Wöhler model, but maybe there must be a way to kind of look at, well, at the same time, we know well the Wöhler model. Well, this one, we don't really know that. But I don't know if there might be a way to look at some version of the Axelrod model that can be thought of as some Wöhler model perturbation where individual would just, interact at rate 1 period, but then sometimes you slightly change the rate based on their culture. So you just have some kind of, like they call like this parameter, like this small perturbation, they call that weak selection, especially in the context of evolutionary game theory. And in this case, that would not be like weak selection, that would be weak homophily or something like that. But maybe, if you look at the Axelrod model without homophily, then that's a nice Wöhler model. But if you include homophily by saying that only, at some very small rate, they would have, additional interaction based on similarities, then you would get some Wöhler model in perturbation that, according to the general work of Cox, Durrett, and Perkins, can be studied using hydrodynamics limits, and you have convergence to some reaction diffusion equation. So that might be one way to go. I don't know.
No, that's very interesting. Yeah, we should talk more about that. Well, we're both in Arizona. Has the Axelrod model been used to study social opinion or social behavior in Arizona? Do you know?
I don't know. I'm not sure. I didn't follow really the work of sociologists. I looked at, of course, the work of Axelrod. I mean, I looked at work of sociologists from those people who also have a strong math background and design models of interacting particle systems. So you have, for instance, Guillaume Desfurn in France, who developed also some very nice model that people studied. But I'm not following with how they use this model like in real life. But yeah, I don't know. Yeah, I'm not sure. I'm not sure.
Well, if there are no further questions, why don't we thank Nicolas again? And thanks, Nicolas, for coming on. And
thank you again for the invitation. I'm going to stop sharing so I can see you a little bit more. Well, thanks a lot. Yeah, that was fun.
Yeah, thanks a lot.
Salut.
Bye. Au revoir.
Talk to you later, Nicolas.
Bye. See you.